I was asked to keep the speakers on time, and I was eyeing this gavel, and unfortunately Michael was precisely on time, so I didn't have a chance. But I thought I'm never going to have a chance to use a gavel in formal setting in my life. I'm not a judge and have no hope of being one, but maybe I'll get a chance to use this if I can keep the speakers on time. So let me introduce our next speaker. Catherine Ordun has led work using natural language processing to study bomb blast injuries for CDC, weapons of mass destruction for DARPA, and data science for the Navy. Currently, she leads data science and surveillance teams for Booz, and she'll touch on the challenges of understanding what's in big data surveillance architecture. Catherine.
Thanks. Hello, everyone. For today's talk, we're going to focus on 3 challenges. The first is going to be to decipher and translate exactly what is in a big data architecture. And I emphasize this point as a little bit of consumer education. While there might be many policymakers, directors, and burgeoning data scientists in the audience, I think it's important nowadays in our big data landscape to have a good sense at a high level of exactly what goes into your big data architecture, rather than maybe just tossing it over the fence to your software developer. The second part will be figuring out where do the analytics actually fit into this big data architecture or this landscape. And then at the midway point of my talk, I'm going to talk about how to build some of these analytics using 3 projects I'm currently working on right now. The first of those examples is natural language processing application, extracting information from social media. The second graduates to something a little more sophisticated, using geospatial analytics from our partners at Epidemico. And then I'll finally cap off my talk with an opportunity that I'm leading at the FDA CEDAR, looking at the RAPID system for adverse event detection. So let's go ahead and get started. Now, this is my sample big data architecture. You might have heard a term called a tech stack. And what I'll do is I'm going to guide you through each layer of this tech stack. Now, if you go onto Google right now and you query big data architecture, you will come up with numerous colorful schematics and diagrams about how other people have laid out this architecture. Well, we'll talk about the sources. This is the actual data that you're analyzing. We'll next walk through the data system. This is where your data is actually living, ingested, processed, and transformed. Above that is a consumption layer, which is a place for business users who are not data scientists or software developers to retrieve your packaged data. And then finally, we've got an API layer that's sandwiched. And you can think of an API as a set of instructions that sends data back and forth between different computer programs. And at the top, I think a lot of you will favorably see a variety of client applications used to create data visualizations and different reports. But this brings me to my consideration number 1, which is one size does not fit all. I was telling you, if you Googled big data architecture, numerous blueprints and diagrams. If you don't take anything away from this talk, I emphasize this number 1 point, which is nothing can begin without a good use case or a research question. In multiple projects that I've led, many of these architectures have failed and not been able to pivot midway through the project because we haven't really arrived at what is it that you exactly want to be doing with your analysis. Starting at our layer in that tech stack, at our sources at the bottom, you'll notice some familiar icons. We have XLS files, CSV files, some flat files. We've also got examples such as Twitter, which is big data. And then we have some APIs that might be connecting and pulling data across the internet. Now, IBM states that we have 2.5 quintillion bytes of data produced every day, and that 90% of that data has been produced in the past 2 years. This brings me to my consideration number 2. How much data do you need to start your project? Many times, if you're starting a new analytics and you're looking at 100,000, 1 million, 10 million records within, let's say, an Excel spreadsheet, that does not constitute big data, but that's okay, because you can still build out an architecture strategy using just a marginal sample of your data. Next, let's talk about the data system. You'll see enclosed in this rectangle, sandwiching the sources and the data system, some colorful icons. You'll even see a little guy with a mustache. And what these are different types of technologies that are available today used to essentially FTP structured data, unstructured data, streaming data like videos or different types of images into your data system. There are so many diverse technologies available today for almost every myriad of data source that you can imagine. Now, once we've brought this data into our data system, we typically house it in the cloud. And in my experience, we've been using Amazon Web Services, or AWS as short, where you host a variety of big data analytics tools. And you've noticed I put an icon here for Hadoop, which is one such tool, and another one called Spark that you might have heard of. And what you can think of is that each one of these tools, Hadoop and Spark, are merely a family of big data tools used to extract, map, batch process, transform, and dynamically be able to change how your data is processed so you can be able to do some analytics on it. Now, Hadoop has been around for a little bit over a decade, is very popularly used across many organizations, but Spark is a little bit of a newcomer to this scene. Spark claims to be up to 100 times faster than Hadoop and is used in our geospatial analytics application that I will show you in my example number 2. Once we have a place for our data to be living, we now get into a consumption layer. And for those of you familiar with big data architecture, this is something a little bit custom and unique to my particular sample. This is a place where you might have some pre-packaged, canned, your top 5 most popular data views. In your project, you might think of 5 variables that 10 of your analysts are always querying all the time. This would be a good place to set up those data views. And I've shown a variety of different databases to potentially put these data views. Now you notice I've got a little indicator that says OR. And what this points out to is consideration number 3. A lot of times in our practice, we're selecting technologies based on our staff preference and our staff expertise. But when you're starting your project, or even if you're in the middle of one and planning to take a different turn, consider the capabilities of the people on your team. And just because you have someone who does not know Hadoop or Spark, that is not a showstopper. In many ways, technologies offer great workarounds. And again, it goes back to my number 1 consideration. Always think about your use case and your analytic question first. Now we go into our API, and as I was indicating before, you can think of an API as a set of instructions that swaps data back and forth from one computer program to another. And I've provided a couple of icons here about what we call web services. This is different ways that APIs are sent back and forth. And where they're sending that data to are our client applications floating at the top. You may be familiar with applications like Tableau and Click that offer some commercial, off-the-shelf, or COTS dashboarding visualization tools. We also have some data science tools that can be placed in this client application, like R or Python. And way to the left, you'll see a red icon that denotes your project. Maybe you're creating a dashboard, perhaps a user interface for some type of machine learning algorithm. A lot of our users would be accessing these client applications through a website or a URL that has your username and password. And they're now able to delve into that data to be able to generate reports, insights, and recommendations. And this brings me to consideration number 4. You've seen a dizzying array of colorful logos and icons. Do not allow these technologies to intimidate you. They are here to play a supporting role. If you do not have that use case and that question defined, then it'll be very difficult to really come up with the technologies to support your end product. We'll move into challenge number 2, which is figuring out, okay, now that we've seen this whole architecture, Catherine, where do the analytics go? And what I've shown you here on this screen is what we can also call a data science pipeline. And we can kick off this process at the sources layer at the bottom that you're now familiar with the exercise of collecting and curating data. This is not a trivial task. In a project that I co-led at the CDC several years ago, about half our time was spent trying to pull 300 different variables from 15,000 different different data sources. So while we're living in an era of openly, publicly available data, it's still challenging to be able to organize it, tag it, and share it in a way that makes sense for your project. Some of you might have heard the idiom that says in data science, 80% of your time is spent doing these unglamorous, janitorial type of duties, and the other 20% is spent doing a lot of fun. Well, the collection and curation begins that unglamorous task, and we move up into the second analytics process of the ETL, the extract, the transforming, and loading. And that's how we use our tools like Hadoop and Spark, either differently or in conjunction with each other, to start that entire process. After we've been able to ETL our data and get it into a place that lives, we can now begin to store it. And this brings me to one revolution in technology. Probably 5 years ago, if you had 1 terabyte of data, it would take about 13 hours to actually run that data set. But now, from my own personal experience, I know that I can run 1 terabyte of data in 5 minutes using one Apache Spark cluster. Oftentimes, the place that you store the data can help also determine how fast and quickly that data will be available. We'll now move into this blue rectangle, and I've provided in italics at the bottom. This may occur locally or outside the system. You might see some people in your team coding furiously on their MacBook. This is usually where that process happens. So a lot of times we're able to do the analysis either locally on our own machine, or sometimes we can take a snapshot of the data and throw it onto a different server within our cloud environment, so you can have a little bit more control over your data science land. We begin this process with wrangling, normalizing, and cleaning it. This is also not a trivial process, and in my personal experience, it can take up to 50% of my analytics time. We can then go into exploring the data. Summary statistics often doesn't suffice. Sometimes it's not just good enough to see your maximum, your mean, or your distribution of values. Exploring data is about understanding the features of the data, mapping it, the relationships and the dynamics of that data set in comparison to another data set. We finally get to modeling. This is where we can do some descriptive analytics, some predictive and prescriptive, and that's how my examples will illustrate some of these models. After undergoing this analytics flow, we can now begin to report, visualize, and recommend and create some interesting graphics, visualizations, and some different types of ways for a policymaker or director to begin to understand and interact with that data. But speaking about data, number 5, unfortunately there is no such thing as a 1-800-statistician hotline, otherwise I'd be calling it all the time. But what this really points to is that you have to consider the limitations of your model. It's almost a paradox that this is a big data landscape, because in many times we can't boil the whole ocean of big data. We have to take a sample of that data. And what's important to realize is that there are limitations. There are outliers, there are clusters, there are rare events, and there's oftentimes missing values. How will you deal with that? When you're dealing with this type of sampling of a big data process, it's important to figure out what your assumptions and your limitations are, because eventually in the end, the confidence that your end user has in the results emanating from your analytic will be based on these assumptions. Midway point through our talk here, and I'm going to talk about how to build an analytics application. And I began with a small scale one where a couple of years ago we used NLP, natural language processing, on 1 million tweets to extract the number of people who are hospitalized, sick, and dead. And I'm going to walk you through this purple arrowed workflow. By the bottom of each one of my example slides, you'll see some of the analytics that we used. First, we brought in our Twitter data in conjunction with some RSS or news feed data. We underwent that process of data filtering and transformation. What this meant is we only wanted to focus on English. We wanted to take out characters like ampersands and quotation marks. And after that process, we then started using an application in Python, a library called NLTK, to do some of these text mining algorithms, such as one called TF-IDF, which is just a weighting algorithm, and then applying some grammar rules so we could translate some of these tweets. Once we were able to extract the number of people hospitalized, sick, and dead, we just threw it up into a commercially off-the-shelf COTS dashboard using some descriptive analytics. And you might find in 50% of your projects, Descriptive analytics are enough, meaning columns, bar charts, different types of histograms. And we used a dashboard called Splunk. And the reason why is, well, we had it available. And it also had a Python backend. So it allowed us to pipe in our algorithm very easily. Now, we tried to do some time series ARIMA modeling, but we just did not have enough data points. So that's going to be something that we'll have to approach later. But when I show you this architecture from that purple workflow, you'll be familiar. We've got the sources. You know about our data system. There is a little area called local analysis, that MacBook approach. And then we have our client applications. And you'll see that unlike a couple of minutes ago when it was full of tons of logos, this is a very streamlined, very vanilla type of view. We have our JSON file of 1 million tweets at the bottom. We've put everything into a cloud architecture, and all it's doing is it's pulling the data into a MySQL database. I then begin to do some programming in Python to do these NLP algorithms, and now we visualize that information through columns and bar charts through Splunk. We can take it one step further and make it a little bit more sophisticated. Another example, which is a classic dashboarding exercise. Instead of using one Twitter file, we're now using different types of data, including CDC data, NOAA or weather climate data, as well as census data, to do some hypothesis testing on multiple types of data sets to create this dashboard that you see in front of you. And what this pipeline looks like is very similar, but has a little bit more diversity. You'll see our different data sources at the bottom. Again, we're still using Amazon. And now we've used our data system as basically a virtual server on Amazon's cloud environment. And instead of using Python, now we're using an application that I bet a lot of you are familiar with, which is R. And using R, we've also brought in some open source, meaning free, publicly available, no-cost applications, such as the powerful D3 JavaScript library, to make some really compelling-looking applications and visualizations. And we were able to serve it all up in an R Shiny dashboard application. This brings me to my sixth consideration. In my 5 years at Booz Allen, I've used this approach very successfully, and you might want to consider this. This is called a minimum viable product. It's an agile methodology term, and this is allowing you to take full advantage of all these different technologies to make the lowest cost, the fastest, highest return application that's possible. And if you look at my image of turning a bicycle into a motorcycle, this is essentially the approach that we've been using. You can create your analytic and be able to do it in sprints or iterations, being able to see it and launch it at any time. And I found this to be very helpful in a lot of my work. In example number 2, we now graduate to some real big data analytics. And our colleagues over at Epidemico have created a geospatial application called HealthFront. And you'll see that in this screenshot in front of you, these are all the different hospitals in Baghdad. And going into the HealthFront application, I could also superimpose terrain, land use, transportation, all sorts of different types of topics of geospatial data. And then on top of that, I could also bring in the hundreds of data feeds from HealthMap to maybe see if there might be a bomb blast, a refugee movement, or a particular outbreak. Within the HealthFront architecture, you can see that it now becomes a little bit more complicated. Again, familiarizing yourself with the sources layer at the bottom, we now have hundreds, and it's not the best represented here, but hundreds of geospatial feeds, as well as bringing in all of the HealthMap event data feeds. And you might have noticed earlier on the API layer was kind of floating up at the top. API layer is a little bit down at the bottom because at this point it's not sufficient to put in one file at a time. These data fields are pulling from places all over the internet, which brings me on my second point here about how this API is standards compliant, Open Geo Standards or OGC. And this is helpful because it allows for all of these hundreds of geospatial data feeds to essentially be singing off the same sheet of music. Here they're using Spark because this is for situational awareness in real time for a complex emergency. And using Spark in a very, very fast distributed processor allows for all this data to be available very quick. Next are the analytics, and what they're basically doing are a variety of spatio-temporal analytics using the tools that you're familiar with as well, like Python and R, but this time querying using a big data language called Scala. And up at the top is the real impact for the policymakers. Here, people are able to use their mobile phone to get a simple report or an alert, as well as a dashboard to see that map that you had seen in my previous screenshot. Which brings me to consideration number 3. Data standards vary across different data types and formats. In the financial industry, they have data standards. Geospatial, there are data standards. And this might need to be considered in your analytics pipeline in that MVP type of thinking before you really start in your data processing and preparation. I'll bring you now to my final example to conclude this talk. I've had the great opportunity to work on a project at the FDA CEDAR called the RAPID system with Dr. Skip Francis and Dr. Lauren Neal. And RAPID provides signal detection of adverse drug events and medication errors through public mobile app reporting. Now, a couple of years ago, if you were a consumer, a prescriber, or a physician, and one of your patients had a rash or a fever from an adverse event, you'd have to fill out numerous paper forms, and then you'd have to fax that in. What this allows is to significantly minimize that process, where RAPID has set up a mobile app on your native iOS application, allowing people anywhere in the public to report their adverse events to the FDA. And what you see before you on this graphic is our heat map of our signal detection. There's a variety of different, what we call pharmacovigilance metrics at the bottom. They are used to, again, sift the noise, the signal through the noise. And this visualization offers for safety evaluators to be able to identify that drug event in a medical emergency. Now, when we started RAPID, this is not hugely complicated. And what this gets to the point is, with an MVP, it's important regardless of the complexity, the scope, or the sophistication of that project. So in RAPID 1, we started with an MVP. And our sources at the bottom are not even big data. They're all flat files. We simply used what we had available, which was an Oracle database. We created some relatively complex SQL queries. We used what we had available, which was an Oracle WebLogic API that allowed us to create some custom dashboard applications and build out our mobile app. And this takes me to this particular architecture, which I'm hoping that you remember from about 15 minutes ago. This is the architecture that I walked you through in the beginning of my talk. So now you see all the different layers, and this is what we're considering in RAPID for phase 3. We're looking at different ways to bring in big data, including news articles, social media, other types of ways that people are reporting their event, like a picture they might be taking about how they're looking after a rash, as well as all these other technologies that we are weighing and contrasting, again, to focus on our use case. And this brings me to my last consideration of the talk. I have not really talked about security, but security is a very critical decision, particularly when you're dealing with PHI or PPI data like we are at the FDA. Now, we are leveraging the FDA GovCloud, and I'm proud to say that we will be one of 2 applications that will ever have been put into the FDA GovCloud. But we've generated a lot of lessons learned, and there's still a lot more learning along the way. As a recap, my summary of considerations, I've bucketed them into 3 different areas. Number 1, please consider starting with a question. A good use case forms the blueprint. Then you can consider the technologies and the data issues. Number 2, this is a team sport. Consider your team's capabilities and never forget to work with a subject matter expert. Even if your subject matter expert is not a data scientist, it's incredibly important to build this team capability as you frame out your architecture and your analytic. And then finally, don't over-engineer. I don't think that we need a self-operating napkin. We need to start with thinking about the use case, and you may not need big data to start. And then you might want to consider the approach that I've been using, which is that minimum viable product, or the MVP. Thank you very much for your generous time. And Scott, I did not collaborate with you about the Nate Silver quote, but I think that it's very relevant for today. Thank you.